That's so cool.
Hey, Jennifer. What's up, Michael? Hey, how you doing, Junior? Just trying out my new guitar. What do you think of it?
It's pretty cool.
Because today, we're going to make a band and learn about sound.
I've always wanted to learn to play the drums.
Well, we're not going to make a band with these instruments. No, we're going to make a band with those instruments right here.
Those?
Sound is all around us. It occurs naturally. Thunder, wind, waves, birds, other animals, and of course humans. Some sounds are man-made, such as traffic, aircraft, machines, but whatever the origin of the sound, it's all based on the same thing, vibration. So now, if you place your fingers on your throat when you speak, you can feel these vibrations. Sound is the rapid motion of particles of matter colliding with each other and passing on energy as a traveling pulse. Sound needs matter like air or water to vibrate and travel through, like waves on an ocean. Sound cannot travel in a vacuum, which has no air. Without air, like in space, they can't hear you scream. Try it.
Like this, Professor?
Yes, that's exactly right. Now say, yo.
Yo.
You feel it?
Yeah, I feel the vibration.
Yeah.
Yodelay-hoo. Hey, I feel it too.
Testing 1, 2, 3. Hey, I feel it.
Let's think about sound waves. First, Jennifer, take this comb and run your finger along the teeth. That's it. You can affect the sound the comb produces by plucking it harder or softer. Now, if you touch the end of the comb to the tabletop, the sound is amplified. See? Because the tabletop then starts to vibrate as well. And your ears pick up all the sound waves. All sound travels at the same speed, 340 meters per second through air at a temperature of 20 degrees centigrade, or for the metrically impaired, that's 1,130 feet per second at 68 degrees Fahrenheit. Now, sound travels faster through materials that are denser than air, such as water. Now, in water, sound travels at a dazzling 1,500 meters per second. So if all sounds travel the same speed through the same material, what do you think makes one sound different from another?
The size?
The shape, maybe?
Well, those are all good answers, and you're all essentially right, but we're going to discuss that in a minute. For right now, we've got a Slinky here to provide a real good example of what a sound wave looks like. Now, stretched from one end, a longitudinal wave is sent along its spring. The vibration is traveling in the same direction as the wave. If the end of it is moved up and down, then a transverse wave is sent along it where the vibration is perpendicular to the direction the wave is traveling. Now, note the highs and lows of the wave, or crests and troughs. These crests show the amplitude or height of the wave. Now, this determines the strength of the sound. Therefore, the greater the amplitude, the louder the scream. We can hear longitudinal waves and transverse waves when we tap on this aluminum pipe. Now, Michael, what I want you to do is take this comb and tap it right here on the side. Now, you hear that? The low pitch is a transverse wave. Now, Junior, take the same comb and strike it right here on the end, okay? Now the pitch is higher, right? Because the sound wave is traveling the direction of the pipe, and that's called a longitudinal vibration. Now, let's do another simple experiment to show how sounds vibrate. Now, everybody take a plastic cup. There you go, Junior, and there's one for you, Jennifer and Michael. Now, take a rubber band and stretch it out and go across the top of the cup, that's it, exactly, and the bottom, just like that. Very good, Jennifer. You've done this before, huh? Now put the bottom of the cup against your ear and gently strum the stretched rubber band. Now what are you hearing? What do you hear, Jennifer?
I'm hearing a sound of maybe a guitar.
Yeah? What about you, Junior? What do you hear?
I also hear a sound. It's just like a banjo.
Yeah? What about you, Michael? What do you hear?
It's the sound of vibration.
It is. Why do you think that happens, Junior?
Because of vibration?
Exactly, vibration, but how is it vibrating? Do you know?
The string is moving back and forth.
The rubber band. The rubber band, it's moving back and forth. It's moving back and forth. You can see it vibrating. It's moving back and forth at a really high rate, but you can see the tiny vibrations in it when you look at it. And what that does is that displaces the air around it, and the cup amplifies the sound. The object moves back and forth. It hits against the air and any other object near enough to be touched. The vibrations cause the volume of air to move and transfers the energy to your ear, which registers that sound that's been produced. Now, we saw with the aluminum pipe, the different waves create different pitches and highs and lows in sounds. Pitch is different than loud and soft, as you can make a high pitch like a flute or a low pitch like a bass fiddle, and they could play either loud or soft. So how is pitch produced? Let's do a simple demonstration of pitch. Now I have a wooden yardstick here, which I'm going to press one end down with my hand to hold it on the table, while I push this end down and release it quickly. Now listen to the sound. Now I'll slide it out quickly onto the table as it moves up and down. What's happening?
The pitch is getting higher.
Exactly. Listen. The pitch gets higher. Now we all know that sound is produced by vibrating materials. The pitch of the sound becomes higher as the number of vibrations increases. The longer the vibrating material, the slower the up and down movement, and the lower the sound. Now if we shorten the yardstick, it moves up and down very quickly and in turn makes a higher pitched sound. Why don't you try this, Jennifer?
Okay.
Here's what we're going to do. You push down on this, right about here, and flip the end of that. Push your hand back here just a little bit more and give it some room. It's going to be vibrating right here, okay? Now you can see it bouncing up and down. Now move it into the table about 3 inches. Now try it. Now move it in about 3 more. That's it. And you can see it's vibrating faster. Can you see it? Mm-hmm. Now let's look at some sounds. This is an oscilloscope, an instrument that displays the patterns of sound waves. The shape of the wave is what makes one sound different from another. These distinguishing wave patterns give each sound its own quality or timbre. Timbre allows us to distinguish the sound of an orchestra. For example, we can tell the difference between a clarinet and an oboe, even though they may be playing the same note. Okay, let's do some other activities and make a few instruments at the same time. I have some bottles and some wine glasses. Now, Junior, you're going to help me make a bottle organ while Michael and Jennifer are going to help get those glasses to sing. Okay, Michael and Jennifer, here are 2 very fine wine glasses. Now, these glasses have been washed and dried, and I want you to both dip your hands right here in the soapy water here. Got a little bit of this Brand X soap. Now, dip your fingers in there, both of you. Can you reach in there, Michael?
Yeah.
Yeah, just get them wet. Take this. That's good. See, you can't have any oils on your fingers at all. That's what the soapy water's for. Now, Michael, take that vinegar and open it up and pour some into that beaker, please. The vinegar will stop any oils produced by our fingers being transferred to the glass. That's good. That's good. That's enough. Now, holding the base of the glass with one hand, both of you guys do this. You take that. I'm going to put a little water in it. Okay. Jennifer, I'm going to give you about this much. Michael, I'm going to give you just a little bit. Now, take this beaker of vinegar and dunk your finger, your index finger in there. Just your index finger. That's good. You do the same thing. Now, gently rub in a clockwise motion around the top of the glass with the tip of your finger. Put it down on the tabletop here, Michael. There you go. That's it. Go around a little bit faster, and we'll see what happens. Okay, now we're going to make a bottle organ. Now we're going to take these bottles and empty their contents into this beaker. These soda bottles here. Do it real carefully. Hand me another one, please, Jennifer. That one. Okay, Jennifer, line up these bottles, please, for Junior. That's good. That one there. Right. Right. Now, take this spoon. Where's the spoon? I got a spoon right here. Junior, please tap on all 4 of those bottles.
They sound pretty much alike.
I'm going to take some black tape. I'm going to put it right here on this one. And I'm going to come up about another inch on this one. And still another inch on this one. Like that. And on this last one, I'm going to put it way up here at the top like this. All right, now Junior, take this funnel and put that in the bottle. Take this beaker of soda. Can you do that? Get your hand around that? It's pretty big. And pour some in there up to the line. Keep going. Keep going. Keep going, a little bit more. Okay, that's good. Now put the funnel in the next bottle. Good. Hold this, here, I'll take this for you. Now, take the spoon and bang on them again and see what happens. What'd you hear?
I hear a different pitch.
Exactly. They all have a different pitch because of what's known as frequency. The number of times an object vibrates and moves back and forth. Now, as the frequency increases, the pitch of the sound gets higher. Tapping on the bottles causes the bottles to vibrate. As the height of the liquid increases, the pitch of the sound gets lower because the sound is vibrating through more of the liquid, like sound vibrating on a longer or thicker string of a piano.
Professor, listen.
All right. So, Michael, what do you think is causing that to happen?
Running my finger along the rim causes the glass to vibrate?
Exactly. Along the rim, it skips and pulls on the glass. Now, this irregular touching of the glass rim is like tiny taps that cause the glass to vibrate. The air inside is struck by the vibrating glass and begins to move in rhythm with the glass. Now, the pitch, the sound that you hear, is due to the frequency at which the glass vibrates. Now, this example of producing sounds is called resonance. Add a bit of water to one of these glasses, and what happens? Now rub your finger around it. What happened?
The pitch changes.
Exactly, just like the bottle organ. Now, here's a few other things that we can do with the bottles. Now here, Michael, blow across the top of this bottle and listen to the sound of the pitch. Junior, you do that too. Now what I'm going to do is I'm going to add a little bit more to yours, Jennifer, and we're going to see what it does to the sound, okay? There, now blow across it. Now yours, Junior. Now they're different, right? Blow them together at the same time, you can hear they're different. Now we're going to pour a little of yours out, Michael. Now blow across it. Now you do yours. And yours, Junior. They're all three different. Now why is that?
Maybe because there's different levels in the liquids.
Well, there sure is. What do you think, Michael?
It's because of the amount.
Well, that's essentially what she said, and you're both exactly right. Now, what you're doing is you're changing the amount of air that you allow in this bottle. You see his? He's got a lot more air than liquid in his bottle. You have more liquid than he does. So, therefore, the air chamber in here is smaller, and the pitch changes. So what have we learned about sound today? It has a speed, which is?
Frequency?
Exactly. And does it move at the same speed through air and water?
No.
No, it doesn't. What are some of the other properties of sound? Junior?
The timbre or quality of the sound and the amplitude or loudness.
Very good, Junior. Well, it looks like you have a pretty good knowledge of sound. All right, let's choose our instruments and make a band. What do you say? Well, I guess we should have learned more about music, but we're having fun with sound, and we learned a lot about that today. Remember, if you try any of this stuff at home, have a grown-up help you out. And remember, science is fundamental, fundamental. Uh-huh, uh-huh, uh-huh.